Hello, Cal State Straub, go Moles. Here we are in section 2 of chapter 11. Yesterday's notes were really long. On one, it was the meat of the entire chapter, actually, so that you can begin to run significant testing. The next two lessons are actually just kind of emphasizing that and throwing in a couple of extra little pieces of information, but nothing as hard as yesterday's was. So to see if you're getting it and getting what we talked about yesterday, our very first warm-up today is going to be this problem. So here you're given a set of data that is actually the difference. So let's look at this. We suspect that students will generally score higher on the SAT the second time that they take the math exam than they did on their first. Okay. Suppose we know that the changes in score, and here these are the second time minus the first time, have a population standard deviation of sigma equals 50. So remember, right now we're just starting with means where we know sigma, although we understand that's highly not as likely. But in this case, you're given sigma. So we know we're going to use Z statistic. We're going to do a one sample Z test, okay, for means. So there's a result here for 46 randomly chosen high school students. And then it asks you to answer this question. Is this evidence that SAT scores increased the second time around? Okay. So remember, we're going to do state, plan, do, conclude, sketch as part of this whole problem to make sure we understand how to do a significance test. Remember, in your state, to state the population and the parameter and your ho and your ha. In this case, remember your null hypothesis, the HO, the ho, the things, the different names that we call it, okay? The HO is that there is no change. So if there were no change in the scores, then your difference would be, hopefully you're thinking, 0. So your null hypothesis should be that the mean is 0. Now we're wanting to say we improved the second time, so think that through, because if you're going to, this tells you it's second minus the first. So what direction should you go from that mean equals 0, either greater or less than that, to show an improvement? Okay, and then when you get to your plan, check your 3 conditions. Your do, use your test statistic for Z, and then write your conclusion and try a sketch. Remember for your sketch that you need to find your new standard deviation, which is sigma divided by square root of n, and you now mark those off across as you go towards where your data point will be. So have fun with that. See how you do. We'll come back and look at my answer key. Okay, welcome back. Sorry again for the mess. These are old things that I just kind of took notes on myself way back and have not redone them for this online testing. But hopefully you got to your state and you made sure you had your population. And sorry about that. I noticed it didn't have it there, so I added it here in blue. It is high school students from a chosen high school. All it says is up here, it is a chosen high school. So high school students from a chosen school. Here's your population parameter. Be sure to list the symbol mu, mean, is the mean change in score on an SAT math exam. Notice it's not the mean SAT math score, it's the mean change, or mean, you could have said difference, the mean difference in the score, okay? We need to put in there what the direction of the difference is also. So it probably would have been a better idea if Mrs. Straub had written second minus first. Oh, I did. It's hiding underneath my blue up here. I thought I had that. There we go. Making sure that you note to the reader that you're doing the difference in the direction of the second test minus the first. Okay. They did not give us an alpha level for this particular problem. So remember, when it's not given, we're going to use alpha is 0.05. We also state what is the procedure we're doing. Just like in confidence intervals, I mentioned that AP likes to see you state the procedure. So we are doing a one sample Z test for means. There it is stated. Also in my state is my HO and my HA, and I already talked to you about the HO being mu is 0 because there's no difference in the scores. And since we're getting an increase in the score, second minus first, we want that mu to be greater than 0. That would show that it is higher. Okay. So we have a one-sided, a one-tailed, right-tailed z-test. Different ways of saying it. Your three conditions, you can see there, all three were met. Hopefully you notice that too with your reasons. Check what I have there. The do, there's your test statistic. Put all this data into my calculator and got an X bar of 13.1. There you could see the work. Sigma was given to us at 50, so we used that. N is 46. So I get a z-score of 1.78, and when you go to the table, that is 0.9625. And of course, we're doing a right tail, so we need to remember to do 1 minus that to get our p-value of 0.0375. So now we go to our conclusion. Since p equals 0.0375 is less than our alpha at 0.05, we can reject HO. And then we need to put that in context. What does that mean in context? So it is likely that students score better on their second try. Because remember, if we can reject HO, then HA is likely. So we need to put that in our context. Let's go on to our conclusion. I wrote it out there. Let's see if I move myself out of the way. Okay. Since p-value is 0.0375 is less than alpha, which equals 0.05, there is significant evidence to reject HO. So this is the way your conclusion should be written. We talked through this yesterday. It is likely students score better on their second try of the SAT math exam. So there's our final conclusion from the test. Now, to get your sketch done, remember we need to go do sigma divided by the square root of n to get our new standard error, which is that standard deviation of the sampling distribution, that S or sigma in the divided by square root of n, and that formula is on your formula sheet. Come here, what is the mu of the claim? That's what goes in the middle, so 0. And then what we got here is marking off 7.37 is our standard deviations. Just keep going. We're at about 1.78, so we know we're less than 2 of those away to get our new X bar here, which is 13.1. So here's 7.37, and then our next one over would, of course, be double that, 14.74, and 13.1 is prior to that, but that should make sense to us because Z was less than 2 there. So we know we're less than 2 standard deviations away. We shade the tail to the right because it's a right-tailed test, and we must put the p-value on it, which is this 0.0375. There you go. That's pretty much the whole thing. If you understand how to do all those steps, make sure you had all those pieces. If you didn't have all those pieces, take time right now to make sure your paper shows these clearly, and you'll have a really good example in front of you for this chapter. So let's go on to just some reminders from chapter 11, starting with our notes here. I'm just reminding you that we still follow the 4-step procedure of state, plan, do, conclude. Make sure in your state that you have stated your hypotheses and that you identify the population, the parameter, and your ho and your ha, right? With your plan, make sure you have your conditions and that you make sure you choose your inference procedure. Your one sample z-test for means, for example, is what we're on right now. We'll be doing t-tests and we'll be doing z-tests for proportions, just like we did with confidence intervals, okay? And you verify those 3 conditions of SRS, normal, and independence, just like we did with CIs. Okay? Calculations. Calculate your test statistic using the formula, which is on your formula sheet in words, and you need to know which symbols to put in there. So you've got the test statistic, and you find your p-value once you have that from going to the z table, or it will be t table when we're doing t statistic. And finally, your conclusion must be an interpretation. It must be in context of what the problem is. You interpret what this p-value means, how it compares to the alpha. you make your decision about whether you're going to reject HO or fail to reject HO. Remember, those are the only terms we use. So it'll either be statistically significant and you reject HO, or it will not be statistically significant and you will fail to reject HO. Okay. All right. And so what we talked about yesterday, there's that test statistic right there for Z when sigma is known. Right now is where we're starting. Okay. And so you will have your different hypotheses for the alternatives, that it'll either be greater than what your claim is, and that is a one-tailed test over there, or it'll be less than your claim if it's a left-tailed test. Or we could have a two-tailed test where you're saying it's just not equal to. So remember, if the context of the problem does not hint at a less than or greater than situation, then you must use the not equal to. And then that's what we talked about at the end yesterday. You have to multiply your probability when you get it times 2. Because when you're calculating this, you're only finding it for one of the tails. And since it's symmetrical, the data is actually in both tails, so you're just doubling it, timesing it by 2. Okay. Caution, as we did yesterday, I mentioned this, but let's just make sure we understand it, that if you fail to get enough evidence against the HO, okay, that means that your p-value is greater than your alpha that you've started off with. So if you fail to get enough evidence, you don't have statistically significant evidence. It just means that the data are consistent with the HO, but it does not mean clearly that HO is true. Because remember, our p-value could be 0.06 and our alpha could be 0.05. That means we don't have enough information or enough data, statistically significant evidence to reject it. But there's only a 6% chance that it could have happened. That's still pretty slim. So we don't want to say that HO is true, just that we don't have enough evidence to say it's not. We don't have strong enough evidence to say that it's not. Remember, the smaller the p-value, the stronger the evidence, because that means the probability is less and less and less that it could have happened by chance, given the claim that you are looking with. Okay. So at this point in time, I had a worksheet out there on your pacing guide. Hopefully you have printed that up. If not, you could just do this work on a separate piece of paper. I want us to do another significance test here and make sure you have all of the parts in it. I'm giving you another chance to do one where I can show you the results and you can get immediate feedback. So, medical director of a large company is concerned about the effects of stress on the company's younger executives. According to the National Center for Health Statistics, the mean systolic blood pressure for males aged 35 to 44 is 128, and the standard deviation of the population, so that tells us sigma, is 15. The medical director examines the medical records of 72 male executives in this age group. Okay, so we have a sample size of 72 and finds that the mean for the sample was 129.93. So your task is to find, is this evidence that the mean blood pressure for all the company's younger executives is different from the national average? Different from, it didn't say less than, greater than, just says different from. So hopefully your mind is spinning. You're going, oh, this is a two-tailed test this time. So my mean, what is the mean of the claim? As you get ready to write your state out, you look up there and you see the mean that was given to us was 128. So then our alternative hypothesis should be that the mean is not 128, not equal to, and we get a two-tailed test. Make sure to state your population and your parameter, your ho and your ha. And then when you get to plan, check SRS. And after that, check for normal, CLT, probably. Looks like a number's good there, right? And then check for independence. And then go ahead and run your statistic. When you're done with that, get your p-value and then write your conclusion. Compare that p-value to alpha was not given, so remember to use 0.05. And I'm going to pause here and let you answer that in Edpuzzle, and we'll come back and look at the answers. All right. Hopefully you were able to set this up. As we look at our state, I see that the population is all middle-aged executives. It was kind of interesting. At first, I said in this company, but it didn't say that they got them from this company. So I think that's an error there. It's just all middle-aged executives. The parameter, and you could have put the exact age, whatever it was, 35 to 44. Okay. The parameter is your mean blood pressure, or mean, you could have said systolic blood pressure. Okay. But as long as you have mean in there in context, we talked earlier about the ho and the ha for your hypotheses. Okay. So let's go to our conditions. Ew, the SRS was not stated. By the way, this is a one sample Z-test for a mean. So you see it kind of, all written along in here. My pointer just doesn't want to show up for me. I think I found it. There he is. One sample, good grief. So it should be one sample Z-test for means. Sorry about all that, making you having to work for it. All right. And then we did say, I hinted earlier that CLT was met for normal and independence. I'm sure there's more than 720 middle-aged executives, even at this company, we're not sure, but in the world there would be. So, all right, we'll assume that. Calculations, here is your test statistic. Hopefully you got 1.09. So we're 1.09 standard deviations away to the right, giving us a 0.8621. Now, why did I do 1 minus that? Because this is a positive z-score, so I'm going to be getting the right tail. When I come up with a negative z-score, I'll be getting the left tail, and I can just use that. But this time I'm over here on the right, okay? And so I'm going to have to, and I just kind of drew a little z sketch for us here. You don't have to do the Z sketch. I just put a Z sketch so we could see we're 1.07 off over here, okay, to the right of that Z score. So we're finding this tail here, and then we can times it by 2, okay, to get that. If you get a Z that is negative, then you're getting that tail, and you'll still times it by 2 to get the total area under the curve. At any rate, there it is, the p-values times by 2, we get p of 2.2758. That's quite large, quite a bit larger than 0.05. So our conclusion will be, since p equals 0.2758 is greater than 0.05, right? We do not have statistically significant evidence to reject HO. Therefore, we are going to fail to reject HO. Okay, we're not statistically significant there, right? And so we'll say that the true mean blood pressure, systolic blood pressure, right, could possibly have been this 128. That there's not enough evidence for us to say that it was different than that. Then the last thing you're going to do is get your little sketch going, and I crammed it in here. Sorry, should have been down here, but your 128 is here in the middle, okay? And then our 129.93 is over here to the right of it because it's higher than it. And we are definitely right at the 1 standard deviation. So you got to do 15 divided by square root of 72 to see what that distance is there. Looks like Ms. Straub didn't calculate that for today. Sorry about that. You would do that, calculate that standard error formula right there, and mark that off on your chart over to get to this value. So think about this. If Z is 1.09, we're only within 1 standard deviation of the mean. So we know that we're getting, we're probably going to be failing to reject that HO. That's a pretty large percent. Okay. All right, let's go back into the notes. Oh, I did this again. Mrs. Straub. Telling me I have to go. There we go. Okay. Just one more concept actually. There's a couple of slides to try and help us get through something that maybe would help us instead of having to run through the whole test sometimes. Sometimes we have a little easy method that we could do. Okay, so let's take a look at this. A level alpha two-sided significance test rejects a hypothesis that of the HO, the null hypothesis, that mean equals a certain factor exactly when that value of mean falls outside of that level 1 minus alpha confidence interval for the mean. What the heck does all that mean? Okay, so if we're doing a two-sided test, what I'm going to show you now only works for two-sided, okay, because that's the same as a confidence interval. A confidence interval is a two-sided, right? You've got data in the tail each way. So if you're doing a 95% CI, then your alpha is 0.05. That's what's left in your tails. So that's what this 1 minus alpha, 1 minus 0.05 is 0.95. So that would be a 95% CI. So if that value falls outside of that confidence interval, then you know that you're going to reject that hypothesis, that null hypothesis. So let's do an example. Let's say you have a 95% CI for the number of games the Chargers are expected to win this year. Okay? Sorry, we're still talking Chargers. Some of you may still be fans, and some of you may be mad that they've left and you don't really want to do this, but we're just using Chargers for now until San Diego gets another team. So you go from 5 to 9. So is your CI. So 7 is our middle number there, our mean, right? Okay, suppose you have mean equals 8 is the claim, okay? And you need to consider whether that is a valid claim or not at the 0.05 level because it was a 95% CI. Your alpha is 0.05, right? And so we look at this and we say, is A in, this is two-tailed, so our ha would be this two-tailed mu is not equal to 8, okay? So do we reject that or not? And I just said, note with your CI, you should have noticed that the mean X bar from the sample was 7 and you've got a margin of error of 2 on each side, okay? Well, the first method that we just talked about and have learned is that you go run your standard error formula, your Z star, your Z formula, right? And you get your p-value and you times it by 2 and we see, get rid of this silly thing here. And we see that our p-value is definitely much higher than the alpha value, so we would fail to reject HO. However, the nice way, if it's two-tailed, we can do this method. Because 8 is within that CI from 5 to 9, then we don't reject HO. We don't need to go through all this math. We can find the claim right here if we know the CI of this. So sometimes you've calculated a CI and then you see a claim for it. You don't need to go do that work again. You could say, 8 is in here, so we will fail to reject HO because it's very possible. Just like you answered on your test questions for me. If it was in, it's possible, likely. If it's outside, it's maybe not so possible, not as likely, okay? It's possible, just not plausible. How's that? So this is called the easy method. So I put an easy button here for us to look at, okay? However, if it's a one-sided test, so here I did the exact same problem, but I just put it one-tailed, less than 0.8, or less than 8, sorry. Do you reject it? Okay. Well, the only method you could use here is the full-on formula. Oops, let me go back. That we just did, finding your p-value for one tail. And notice it's not times by 2 now because it's just one tail, but it's still bigger than 0.05. So we would fail to reject HO. So again, one-tailed, don't have the easy method, but two-tailed. So let's go back one more time and look at one just slightly different. Here's your CI of 5 to 9, a 95% CI. We have a claim that the mean is 10. Okay? The mean number of games they could win is 10. So if our alternative is, I don't think they'll win 10, but we don't have a direction for it. If it's two-tailed, then the alternative is mu is not equal to 10. So would you reject the HO? Sounds kind of bad. We reject the HO at mu equals 10. Okay. Well, is 10 inside that CI? You could go back to your method one that we've been talking about. There's your Z statistic showing you that you get a p-value of 0.0016. Dang, that is pretty small, even when I times it by 2 for my two-tailed. That's still less than the 0.05. So I would be able to reject the null hypothesis that mean is 10, and I would conclude the mean number of wins for Chargers is not likely to be 10. Okay, so that will still work. I'm just showing you how it compares. However, the fastest, easiest way is to say, this is a two-tailed test. I'm looking at that CI. 10 is not in that CI, 5 to 9. So we're going to reject HO at the 5% significance level and be done with it, which would mean that it is not likely that the Chargers will win 10 games. Okay, super duper easy, I hope. All right. So one last look at this concept. Just, I don't know, there's the one-tailed test with the 10 now. So what would you say as you look at this? You have the same CI that I gave earlier, 5 to 9, and your claim is that they're going to win 10 games. And your alternative is, no, I think they're going to win more than 10. So what's the likelihood of that? Would you be able to reject HO that it is 10? So check that out. Do that problem and let me know. I'll come back and check with you. All right, the only method you could have done here is method 1, finding your z-score. So here's your z-score. And since it's one-tailed, right-tailed, we're going to subtract that from the 1. That is definitely bigger than 0.05, so we will not reject HO. And we're going to conclude that the mean number of games won was not likely greater than, let's see, we're not rejecting, Mrs. Straub, we failed to reject HO, that it is 10. Okay, so we have to conclude that it was not likely going to be greater than 10. We cannot accept the alternative because we cannot reject the null hypothesis. I don't know what I said there. Hopefully I said the right thing. Okay. So here's your same CI at 95%, 5 and 9. And if you had the null hypothesis mu is 10 and mu is less than 10, would you reject it? Again, this is one-tailed. So this time we run it, but this time our z-score is the same, but we're not subtracting it from 1 because we're going to the left, correct? This is less than 10. So in this point, we would have a number less than 0.05. At this point in time, we would reject HO and we'll conclude the mean number of games won was likely less than 10. Okay, so we have enough statistical evidence there to reject HO when we went less than 10, but we don't have enough evidence, obviously, to say that they're going to win greater than 10. Sorry, LA, you got the team, but they may not win that. Okay. Hopefully you see the difference between left tail, right tail, and how to operate those tests, along with two-tailed tests and how they connect with CIs. All right, we're done. Do your homework and check some of these questions and jump in on the next conferencing time to get your questions answered, and I will see you then. Have a good rest of your day, guys. Sure miss you.